Okay, go ahead with your question.
For the first question, it says to talk about the packages, but can you just explain briefly for me what he means by packages?
Basically, these are like what we talked about in the resistors. It's like the kind of, for example, if you have surface mounted, you have different packages for the surface mounted. Remember, we have in the resistors, we saw different packages. We have the through hole package. We have the through hole also has different packages like axial or basically radial leads. You have also, if you have multiple resistors, you have dip package, you an inline package or a single inline.
Okay.
You have surface mounted, you have PLCC, you have different packages for the different kinds of components. So basically,
So like the different types of resistors, right?
not resistors, it's generals for all types of components.
Ah, okay. I thought
Basically, you're talking about ICs, you're talking about every kind of component, basically. So, for example, if you look at the processor you have on your computer, you know that it's basically what's called the ball grid array. It basically has leads underneath the component, and there are so many of them, like 500 of them. Like that. It's like an array, a two-dimensional array of points that are basically connected to the inside of the integrated circuit itself. So basically, look at things like that. Okay.
Okay.
There is one of the resources I uploaded for you is one of the lectures I had before on my YouTube channel. It talks about electronic components, and basically the first part of it actually has some explanation about what packages mean and gives the examples of different kinds of packages. So basically, you can also look at this presentation, and basically it can give you some clues on how to solve this particular problem. Okay?
Okay, I'll take a look.
Okay. So far, I haven't heard about the groups. Basically, you're supposed to form groups of 4 to 5 students so that you can start working on the project. If you already
had
send me your group, okay? Send me a message, an email, or whatever, or a WhatsApp message. Just send me the group that you already formed. I would like to know
I'll
exactly
send you an
who
email.
started and who didn't start. Okay? Because I would like to contact those who didn't start because actually we don't have much time.
Okay.
Okay, so basically by mid-April, we have to finish everything. We have to be done with everything, okay? Including the project, including the final exam, whatever they are going to decide about. Basically, we have to be done with everything by Shaban 23rd. So basically, be sure to get started on the project because you don't want to do the project in one night or something like that. It's not going to finish. It's not going to be complete in one night. Okay, you have to get started and you have to divide the questions between the different members of the group so that they can actually do their search and basically collect everything together and send it to me. What you will have to do is for each member who works on a particular question, he has to explain it to the rest of the group. Because what you're going to have is an exam about all questions for each one of you. You're going to have like MCQ exam about the project. Okay, this is one part of the project evaluation. So basically you have to at least understand what each part is all about so that you can answer questions about it. The exam will be basically open report. Basically, you will have your report with you and you can look at it if you want, but you have to understand it. You're not going to read it during the exam, basically. You have to read it before, you have to understand what was there in order for you to get to the answers very quickly. Any other questions?
Doctor,
go ahead.
روح يا سليمان.
روح خلاص.
Okay, Doctor, I want to ask you about the PCB footprint in the capacitor because I didn't understand what.
Okay, this is related to the same issue actually. Basically, this is in the project also, right?
Yes.
Okay, let me get to the resistor presentation and show it to you, basically. The footprint meaning that the size of the component itself. Okay, let me show you an example here. Can you see the presentation here for the resistors? Can you see it?
Yeah.
Okay. See these components? Okay. They have different sizes. Okay. See here? This one here is 0402 has a very different footprint from, for example, this 1206. They are both resistors, by the way, but actually have very, very different footprints. Footprint meaning that basically it's like if you look at the area of the component itself, this is the footprint on the printed circuit board. Okay, so basically when I'm asking you about the smallest component, the smallest footprint, for example, you probably should try to get, you know, the smallest possible package for a capacitor. Okay.
Okay.
By the way, I would like to let you all know, when I ask you about the smallest, okay, it's not an absolute. I'm not gonna basically grade you for a particular package that I know, and basically if you didn't get it right, I will give you a 0. No, it's not gonna be like that. Just do your best and get the smallest package that you can come up with, and this will be fine. So for example, if somebody came up with 0603 and somebody came up with 0402, they would both be okay, okay? I just wanna basically make sure that you understand the meaning of the word footprint and that you actually made an effort to find a component with a very small size. Basically, yeah, that actually makes sense, basically. If you come up with something like this, for example, diff 18, it doesn't make sense, okay? But any one of these small ones would be okay, okay? So as long as you put an effort and basically came up with something that makes sense, you'll be correct. You're not gonna be graded based on particular answers that I expect you to get, okay? So I will look at what you have and I will grade you based on the effort, not based on exactly what the answer was, whether the answer was the absolute best answer or not, okay? So do you understand?
Yes. Yes.
Any other questions about the project?
Doctor?
Yes.
Should we like solve it or like write it as a report or just you know, answers to the questions? Basically just answer
the questions, basically. The report itself is just answers to the questions. You don't have to format it like introduction and it's not like a paper or something like that. It's not like the project report or something like that. Basically, it has to be just answers, a collection of answers to each of the questions that you have in the project.
Doctor?
Yes.
For the exam or for the test on the project, the questions will be general for everyone or each group depending on their...
Actually, basically the question will be very general, okay? But actually, I just wanted to make sure that you understood the questions and basically you know exactly what you have, what you did basically in your report. For example, if I ask you about a small package, for example, okay? The smallest package or the package with the smallest footprint, for example, okay? I will give you, for example, some examples, maybe some examples from here, okay? And basically ask you which one of these is basically the smallest, has the smallest footprint. Okay?
Okay.
It should be general. It should be general for all of them. But actually, they will be directed towards the idea behind each question, not exactly what you answered in each question. I just wanted to make sure that you understand the meaning of what I was asking about. Any other questions about the homework, about the project?
دكتور بالنسبة دكتور
ايوه اتفضل.
بالنسبة له حيكون بالتنسيق مع المهندس طريقة
التسليم. هو المفروض المهندس the engineer was supposed to contact you. I'll contact him today and by Thursday you should get whatever you're supposed to be working on, okay? The experiments, from what I understood from the engineer, that you were doing the simulations in each one of the 5 experiments that you already done. Okay?
Yeah, from 1 to 5.
Right? Okay, so basically the last two experiments will be just a simulation without the actual experiment. So this should be very simple for you. Okay?
Okay.
And after that, you'll have a very simple, basically an exam on Blackboard, a very simple exam on Blackboard, just to get the part of the exam, the part of the lab exam done, basically at the end of the term. So basically, this will be very general questions about how to use the measurement equipment, some of the questions related to the actual experiment, things of that sort, but just to make sure that you understood what you were doing. Okay?
Okay.
So inshallah, by Thursday, the lab will be actually, everything regarding the lab will be very clear to you. And I also asked the engineer, once you deliver your report through Blackboard, he will give me the grades so that I can post it for you. Some people actually asked about the grades for the experiments because they were worried about basically getting the grades too late, and they might have lost some points or something like that, and they might not have the chance to talk to the engineer about them. First of all, don't worry about the grades. Basically, the engineer Mutahir usually gives good grades first of all, and basically I'll make sure that you get the grades early on, so that if you have any complaints, we will deal with them, well before the end of the term. Okay, don't worry about that.
Okay.
Okay. You have any further questions, or should we get started on the presentation, on the lecture? Okay. So
Doctor, I have a question about the homeworks. Are the grades how's the system of the grades for the homework?
What do you mean the system of the grades? You know how much points, how much marks for the homework as a whole? Actually, you can look at the syllabus. The syllabus has the division of the 100 points for the whole course between the homework, the project, the lab, and the midterm and the final, basically. Okay, so we'll have the division. The homework usually has 10%. Okay, so very much if you have basically you're going to have 8 homeworks, at least 8 or 9. So each homework has almost 1 point, basically. So as I told you before, the grades for the homework are not as big as you think, but they are important for you to learn the material. It's very important for you to try to get good grades. If you get like 80% average in all the homeworks, I assure you that you'll get almost 10%, the 10 out of 10, okay? Or at maximum 9 out of 10, okay? So basically, the homework grade is not as large. So basically, you're encouraged to try to solve them yourselves, so that you can learn the material. You learn how to get the ideas right, or try whatever you understood from the lecture. Try it in the homework so that you get feedback in order for you to learn your mistakes, basically. Okay, so. Some people actually just basically ask their friends and get the answer and just submit it. They will not learn, basically. They will make the mistakes during the exam, which will be much more severe, actually. Okay, for example, the final exam has 4 times the grades of the homework during the whole semester. Okay, so basically, if you make a mistake in the final, you might lose like 5 points. 5 points is like the grade of 5 homeworks. Okay, so basically, what you're supposed to do is to try and basically test what you understand in the homework without having any worries about the grades and how many points you lose or anything like that, in order for you to get feedback, to know your mistakes and correct them. Okay?
Okay, thank you, Doctor.
Okay. Please don't worry about the grades. If you ask your colleagues from past semester, or if you ask your colleagues from biomedical engineering, they will tell you that I'm very flexible with the grades. The most important thing for me is to make sure that you try to understand or try to learn as much as you can, okay? So basically, my exams are long. material. Sometimes I add some additional material. So basically you have basically more to study and more to work with in the exams, but you usually get much higher grades than the classes where you actually have less material or basically shorter exams. Okay, so don't worry about that. These are basically, they are intended for you to learn more. That's it. And basically what you're gonna come out of this class with is not your grade, is what you learn from this class. So just focus on that. Okay, so last time we stopped at this point here. We're going to talk about the energy stored in a charged capacitor. And basically from what we learned before, power is basically V, the voltage, times the current, right? This is basically the basic part of what we saw before in the first chapter. So basically, if you substitute here V as if you substitute here I as EI, basically is dQ by dt. Basically, if I is dQ by dt, let me write it down here. You can write it down in the notes so that you can see it later. Basically, we have Q is equal to C times V. So basically, dQ by dt, which is I, would be equal to, C is not basically going to change, C is a constant, so basically going to be like this, dV by dt, okay? So basically the power would be equal to V times I, which is going to be basically, if you just add this here, is going to be basically C, V, dV by dt. And if I want to compute the energy, energy is basically the integration of P dt. Okay, you can multiply by time if it's constant, but actually for this here is going to change with time. The current will change with time, basically. If you're trying to discharge a capacitor, the discharging of the capacitor will change with time because actually it's not a constant. The power here is not a constant. So when you try to get the energy out of the power, you basically integrate the power, okay, as a function of C dt. So basically it's the integration of C. You can take C out because it doesn't depend on the time. It's going to be like this, the integration of this, basically. And basically, this will go with this. And if you have integration of V dV, it's going to be what? Integration of V dV.
V squared.
V squared over 2. Okay? Why? Because basically, if you differentiate this, it's going to be 1/2 times 2V, right?
Basically V.
So basically, it's going to be like this. Okay? So basically, it's going to be CV squared or 1/2 CV squared. Okay? So basically, this is the total energy stored in a capacitor. This total energy is basically, this is one of the questions that you will see in the homework. If, for example, I have a particular capacitor here with a particular charge of V here, V naught, for example, okay, then it has basically an energy of 1/2 C V naught squared, okay? If I contact, or basically if I connect this to a resistance, okay, R here, if I just flip the switch on, what's going to happen here? The energy will basically this will discharge in the resistance as we saw last time. And this discharge will make the energy here become less because V here is going to go down all the way to 0 actually, okay? So basically the electrical energy stored in the capacitor, where would it go? We know that the energy basically it does not vanish, it goes somewhere, it's converted from one form to another. So where would you expect the energy to go? So where the energy is going from here? So basically it's going from this here, the energy on the capacitor to what?
The energy on the
resistor.
Okay, exactly what in the resistor exactly?
Heat.
What's going to happen in the resistor actually?
Dissipates as heat.
Right, dissipated as heat. So basically it's going to go down as heat in the resistance. So basically it's going to be what's here? It's going to be basically, if you just take this form, this exact form E, if I basically let the capacitor discharge completely until 0, then this total energy here will be converted to heat. Okay, and this heat will be basically I square R or V square over R or whatever, but actually I here is dependent on time, basically, because the I here will be what? Will be like this, right? It's gonna start from a maximum of V naught over R and go all the way down to 0, right? This is I of T. Okay, so basically what you'll need to do here, this is I square R, this is the power. If you integrate this with respect to time, you will get the total energy, and it's going to be exactly E, because actually this is the only way that the energy will be converted. This is the only way, this is the conversion of the total electrical energy stored in the capacitor into a heat energy in the resistance. Okay, so basically, whenever you're asked about the conversion of energy from one source to another, just consider basically that the energy has to be exactly the same, like what we saw before in chapter 1 when we were talking about the potential energy and the kinetic energy. Remember that? We were talking about basically a certain weight that was lifted up from the surface of the earth to a certain height, and we let it go from there. Basically, it's going to start from a high potential energy up in that position, and basically convert this potential energy to kinetic energy until it goes down all the way to the surface of the earth. Right before it hits the surface of the earth, the potential energy will be 0, and basically the total potential energy was actually converted to kinetic energy because of the acceleration of the object from the original position to the ground level. Okay, so it's exactly like this here. Okay, so it's very important to consider that we have energy stored here, and basically we're going to deal with that and basically use it in several applications. If I have, let me give you an example. What if I have two capacitors like this, C1 and C2, okay? What is the total energy stored in both capacitors? What is the total energy stored in both of them? How we can compute it? Basically, it's very simple, actually. What you need to do is get the C equivalent. Just use this equation. Okay, once you get the equivalent capacitance, basically the total energy is 1/2 C V square. V total here. Okay. If I ask you for this particular example, if I ask you about the energy stored in C1, energy 1 stored in C1 and energy 2 stored in C2, how can we compute that? So now I know the total. This is the total for both of them. How can we do that? Remember how we computed the voltage across the first one and the voltage across the second one?
I need to get capacitance equivalent.
Actually, no, for energy 1 in C1, if I wanted just to get the energy here, I need to get V1 here. Remember?
Okay. Yeah.
How can we get the V1 here?
By voltage divider?
Yes, it's right, but it's opposite from the usual voltage divider of the resistance, if you remember, right? One simpler way, actually, is if you have the total voltage here and you have the total capacitance here, what you can do is compute Q. Q is equal to C times V, right? V total. Let's just call this V total, okay? Okay, right? This Q actually is exactly the same for all of them. It's the same for C1, it's the same for C2, and it's the same for all of them, for both of them. So basically, if I want to compute V1, Q will be equal to C1, V1. If I want to compute V2, Q will be equal to C2, V2. Okay, so basically I already have that, I can compute this, I can compute that. Once I computed V from here and there, I can compute E1 as C1 1/2 C1 V1 square, and E2 will be equal to 1/2 C2 V2 square. This method is kind of easier. Basically, it's easier than the other method, the potential divider, because actually it's more general. Basically, what you're gonna see in the homework is that you will have 3 capacitors. Okay. Let me show you the homework problem. The first homework problem, actually, you have 3 capacitors of 2, 3, and 6. And basically, you're asked to compute the charge, first of all, and the voltage across each one of them, and the energy stored in the 6 microfarad capacitor, in one particular one of them, basically one particular capacitor. Okay? So basically, if you have 3, you're not going to be able to use the potential divider kind of relationship to compute the voltage on each one of them, because you have 3 of them now. Okay, so basically it's easier if you just compute the charge first, and basically this homework is intended for you to go with the charge first, so that it gives you a hint to use that charge, and basically from that charge you compute the voltage across each capacitor, and then once you have the voltage across each capacitor, then the energy in each one of them will be the 1/2 its capacitance times its voltage squared. Okay, is that clear? Do you have any questions about this homework problem?
Oh, clear.
No, it's clear.
Okay, this homework problem, by the way, is due next week. So basically you have next lecture, the lecture on Sunday, and probably also the lecture on Tuesday. If you have any questions about it, please ask me. I actually reduced one of the questions here, so basically I'm going to upload this new version of the homework today. I had 4 problems, but actually I thought you probably loaded with so many things. So basically 3 problems should be enough. So basically you're going to have an updated version of this homework uploaded today. Okay. So let's go back here. So basically the energy is 1/2 CV squared, as we talked about. As we basically derived it, basically. And basically this is very important to know that basically this is an electrical energy, and whenever you're discharging the capacitor, you're basically taking out of this energy. You're basically draining this energy stored in the capacitor, because when you're discharging the capacitor, you're reducing V, and basically you're reducing the energy stored in it in sequence. So here we have, you have a question?
No.
Okay, so let's go through this example. A 50 microfarad capacitor is charged from a 200 volt supply. After being disconnected, it is immediately connected in parallel with a 30 microfarad capacitor with its initially uncharged. Okay, find the potential difference across the combination, the electrostatic energies before and after the capacitors are connected in parallel. Okay, how can we solve this problem? Okay, so basically you have a particular capacitor that was charged. Basically assume that you're charged to this particular voltage. Okay, after you charge it into 200 volts, you're going to connect another capacitor to it. Okay, you're going to connect another capacitor in parallel with it. Okay, so basically let's go and try to solve it.
Doctor, what's the meaning of PD?
Potential difference. I'm sorry. The textbook actually uses this a lot. Okay. Potential difference, PD, is potential difference. This is one of the common abbreviations in the textbook.
Yeah, sorry. I forget it.
That's fine. Okay. So basically you have a 50 microfarad, okay, capacitor that was charged to 200 volts. It has an initial voltage of 200 volts. What you did is just connect another capacitor in parallel with it, okay? Okay, this, I think it was 30 microfarads. Let me check. Yes, it's a 30 microfarad. Okay. Can you see the drawing here?
Yes.
Yes.
Okay. So basically, he wants to know what's going to happen after you connect these two together. Okay. For some reason, the solution in the textbook actually, to me, actually doesn't make much sense for some reason. So basically, I wanted you to think about it in a more general fashion. Okay. So basically, here you have a particular energy. The starting energy before you connected the second capacitor will be what? Energy initial will be what? 1/2 times 50 microfarads times V squared. Right? When you connect another capacitor here, you expect a part of this energy to be basically just vanish. You expect it to vanish so that you have different, basically you have different energy after you connect these two together, or what?
Should start with 0, I think, and then like the energy.
Basically, this actually has an initial voltage of 0, of course, and something will happen here so that you will have basically, you will have a balance between these two capacitors, you know, in order for you to maintain the steady state condition. If you have a 0 voltage here, if you have the voltage here is 0, the initial voltage is 0, it doesn't make sense to have 200 volts connected in parallel with 0 volts, and this will remain the same. They will never remain the same, okay? Because there is a potential difference here. The problem is that you have a 0 resistance between the two. So basically what's going to happen is that basically the charges will somehow distribute between the two. And basically what's going to happen is that at the end you might have a different energy. Okay? So what's going to happen here? What do you expect things here to happen? What do you expect? What's going to happen here between these two capacitors when you connect them together?
A part of the energy in the 50 microfarad.
Definitely this will happen. Definitely this will be the case actually. But actually what you have here is basically you have certain charges here. You have certain positive charges here. You don't have any positive charges here. The positive charges here are 0. So basically what's going to happen is that these charges will be basically divided between these two. Okay? And they are going to be divided in terms of what? You'll be divided, you'll be divided based on what? The voltage will have to be exactly the same, right?
Yes.
What?
Energy.
Go ahead. Go ahead.
They'll be divided depending on energy.
First of all, we have two conditions basically, okay? We have the voltage will have to be exactly the same. V1, let's just call this C1 and this C2, okay? V1 should be equal to V2 because actually they are connected in parallel. This is a condition that we have to make sure it's going to happen. Okay, but it's not going to be divided. It's not going to be 200 first of all because actually this capacitor doesn't have any charges. So what's going to happen is that the Q here, the charges that are present here, will divide between these two in such a way that the voltage, you know, across both of them will be equal. Again, basically, what you have here, V1 has to be equal to V2 because basically they are connected in parallel. The second condition is that you have a certain amount of charges here, right? Okay, the initial charges, basically the initial charges that we started with will be basically divided by the two capacitors. So basically the Q initial will have to be actually equal to Q1 plus Q2. Okay? After we connect the second capacitor, okay? So basically, we have to use these two conditions in order for us to get the voltage and the charge on each one of them, okay? Let's try to solve that, okay? So basically, if I told you that Q1 is equal to C V1, okay? And this one, C1, V1, okay? And this will be equal to C2, V2. And basically, V1 and V2 will be equal, basically, okay? So this will be equal to C1 plus C2 times V, which is, I don't know, basically, okay? And the initial charge here will be equal to what? What's the initial charge? From here.
C equivalence multiplied by V.
The initial charge will be basically C, which is a 50 microfarads, times V, which is the initial 200, right? So you have the initial, this is the initial charge that you started with. So you have that, and you have that, you can compute that. Okay? Is that clear? You started with a particular, before you connect the second capacitor, you already have charges here. The charge is here based on the information, this is C and this is V. And basically the charge is, by definition, is equal to C times V. So you can compute from this the initial charge. This initial charge will be divided by capacitor 1 and capacitor 2. The charge for capacitor 1 is equal to C1 V1. The charge for capacitor 2 is equal to C2 V2. And we agree that V1 has to be equal to V2 because it doesn't make sense to have two components connected in parallel with different voltage difference across each one of them. So basically, you can have an equation here that you can solve, given that you have C1 and C2. You can compute basically based on, you have Q already, and basically can compute how much V will be after this particular connection. Okay? Once you do that, you already computed already the voltage that is across each one of them. And basically the total energy after will be equal to what? 1/2 C1 V square plus 1/2 C2 V square.
Yes.
Is that clear?
Yes.
Okay. Let's go back. One important aspect of the capacitor that might not be, I don't think so many people actually think about it, except for very large capacitors, is the force of attraction between the charged plates. Basically, you have charges, you have opposite charges on each one of the plates of the capacitor. You have two plates, with one with positive charges and one with negative charges. So there must be some electrostatic forces that actually attract them together. Okay? So basically there is a derivation actually, but actually this derivation is kind of involved. It's not as easy as you might think. So basically let's just get the result out of it. Basically, there is a force. This is indeed a force between the two plates of the capacitor, and this force is equal to 1/2 epsilon. Epsilon is the epsilon naught epsilon r, as we saw before, times the area of the plates, times V over X. V is the voltage across the capacitor, and X is the separation distance between them, okay, squared. So basically, whenever you have a particular capacitor with a particular voltage on it and a particular area and a particular separation distance, you can actually use this equation to compute the force of attraction between the plates of the capacitor. This can be actually very important for capacitors holding very large voltages, okay? When we first started talking about the capacitor, I'm probably going to talk about it again by the end of this lecture. One of the applications of capacitors is in the area of defibrillators, the DC shock defibrillators, the Leia Jihaz Sadamat, okay? We actually charge that particular device with kilovolts. Actually, you might find in X-ray imaging systems that are used in the airports or used in the medical imaging field, you might have actually capacitors basically holding hundreds of kilovolts, okay? So you have a capacitor holding hundreds of kilovolts, you actually have to worry about this kind of forces. Because basically this force is applied on the dielectric in the middle between the two plates. Unless the dielectric can withhold this kind of force, it can be a problem actually. Because if you put the higher voltage than what you can actually withstand, you might end up with a situation where you have, you remember the accidents that we talked about at the first lecture. Basically, this is the basis of the rating of the voltage for the capacitors. Okay, so basically the rating is based on what you can actually withstand. If the dielectric cannot withstand this kind of force, what's going to happen is that this force will overcome the dielectric, and basically you will have a short circuit inside. And this short circuit is responsible for the kind of fires or kind of explosions that you actually saw in the videos that we showed in that first lecture. So basically, that force is very important. It's not actually probably not for you. It's probably more important for the manufacturers of capacitors. And it's important for you to realize that if you put a higher voltage than the rated voltage, what's going to happen is that this kind of force will actually destroy your capacitor and might actually destroy some of the components or some of the circuit boards where the capacitor is actually located. Okay?
Okay.
One very important issue also related to the voltage, the rated voltage of the capacitor, is the dielectric strength. The dielectric strength, we all saw basically in the circus or on TV, if you have high enough voltage, you can actually create a spark, okay? There might be some kind of a breakdown of the dielectric material, and actually you might see something like a spark or like an arc, basically. This is basically the basis of, or not the basis, basically this is what happens in the lightning, okay? When you have a lightning, you have a very high buildup of voltage in the sky and basically in the clouds. And basically whenever you have a dielectric, whenever you have a conductor that is close enough, you might have actually arcing between the cloud and that particular conductor. And whenever that arcing happens, this is basically breakdown of the insulation of that medium. Breakdown meaning that if you have an insulating material, breakdown meaning that something will happen, and this thing actually will cause electricity to flow in very large currents through that particular medium.
Doctor?
Okay. Yes.
So it's like shorting the capacitor, right?
Basically, no, not shorting. It's basically, yeah, this will actually do that. If you actually apply higher voltage, basically high voltage than the rated, something like that will happen, okay? But actually, basically, it's like, it's not just shortening. Actually, what's going to happen is going to be much more catastrophic, because usually this kind of currents will be very high, and this will likely, basically, when you flow a very high current through a material that originally has very high resistance, what will happen is that you will generate enough heat to burn that particular capacitor. This is one of the things, one of the causes of what we saw in the videos. Okay, so basically we have to make sure that we don't break down, we don't actually exceed the rated voltage, because you don't want to have that to happen. Okay, and for the manufacturers of the capacitors, they actually, one of the things beside the force, one of the things that they determine the rated voltage based upon is basically the dielectric strength. Let me give you some examples. If you have air, actually the dielectric strength is basically given in megavolts per meter. Megavolts per meter meaning that if you have, for example, 0.2 millimeter thickness, you multiply that by 10 to the minus 3 to get it in meter, and multiply by that to get the voltage in megavolts, okay? And if you put that megavolts across this distance, you will have arcing. Basically, it's gonna basically arc. Arc meaning that you will have breakdown of air, and you will have flow of current through the air across this particular gap. Okay, so as you see here, for air, you basically have very small values here. If you go to Mica, Mica is basically, as we saw before, some types of capacitors I call Mica capacitors. Mica is basically the type of insulation or the type of dielectric that is used in this particular type of capacitor. For mica, you will have a little bit more. Basically, you have 200, basically. So basically, you can have much smaller thickness, and basically, you can actually manufacture capacitors with much higher values if you use mica. If you use ceramics, for example, you have 50. If you have transformer oil, you can have like 200, okay, and so on. So basically, you have for different materials, you have a particular dielectric strength that you have to take care of. You have to basically stay clear of in order for you to prevent any breakdown of the dielectric strength. Okay, so basically, if I told you that I actually I'm designing a capacitor with the air as a dielectric, okay, and I'm going to put a distance of 1 millimeter between the two plates. Okay, if I have 1 millimeter and I have dielectric strength of 4.46 megavolt per meter, then if I multiply that by 10 to the minus 3, this would be what? 4.46 kilovolt. Okay, so the capacitor, if I exceed 4.46 kilovolt, you will have arcing. Okay, basically you multiply the thickness by the dielectric strength to know exactly the maximum voltage or the voltage where the arcing will happen. Okay? Is that clear?
Yes.
Okay. One other aspect of capacitor, as we talked before, we have like basically we assume that the capacitor is just a capacitor. We assume the resistance is just a resistance. We're going to assume that the inductor is just an inductance, but usually you have some other aspects of the same components, and basically they affect the operation of these components. For example, basically the dielectric, as we said before, we never have a dielectric of basically infinite resistance. It has very high resistance, but basically it's not infinite, meaning that if I actually want to model a capacitor, it actually looks like this. It's a capacitor, and basically the resistance between the two plates through the dielectric is a resistance, is a very high resistance, but actually it's there. Okay, usually it's like 100 mega ohms. Okay, but this 100 mega ohms, it might not be much. It might not. You can actually assume that it's infinity, but actually, if you're basically if you have this particular capacitor charged to 100 volts, for example, this 100 volts will discharge very slowly through this resistance. Basically, just imagine the capacitance as your battery, your laptop battery, or your phone battery, your mobile phone battery. Okay, it actually acts like a capacitor, exactly like a capacitor. When you're charging your mobile phone, you're storing electric energy in the form of something like a capacitor, basically in order for you to use it later. Okay, and basically, if you leave your mobile phone, basically without using it for 1 day, you expect to go back and find it 100% after you charge it? Does it stay 100% even if you don't use it?
No.
No.
Even if you turn it off, even if you just completely turn it off. Okay, if you turn it off and you leave it for a few days, you're gonna come back and find it like 50%. Okay, this is because you have a leakage current. Leakage meaning that basically the current leaks between the two plates of the capacitor through the very high resistance of the dielectric. Okay, it's a very small current. It doesn't affect the normal operation. If you're using your mobile phone a lot and basically you're charging every day, you're probably not going to notice that leakage, or it's not going to affect you by much. But actually, if you want to charge a capacitor and leave it for a long time, this would be actually a major issue. Okay, so basically, let's get an example just to see it, maybe in the homework. In the homework here, you have, I'm going to talk about this problem later, but actually for this problem here, you have a 20 microfarad capacitor that has an insulation resistance of 50 mega ohms, measured between the terminals. If the capacitor is charged off a DC supply of 230 volts, this is the initial voltage. you want to know the time required for the after disconnection from the supply for the potential difference across the capacitor to fall to 60. Let's go and basically try to solve it. Basically, we have 20 microfarads. Charged to 230 volts initially. And basically, it's connected now to the leakage resistance of 50 mega ohms. You can see now from just the values of the resistance and capacitance, basically, you're going to have definitely a discharge here, but it's going to be very slow. The tau here will be what? RC will be what? 20 times 10 to the minus 6 times 50 times 10 to the power 6 is going to be what? 1,000 seconds. 1,000 seconds, meaning that it's actually very long. So basically, you're talking about maybe 15 minutes, something like that, maybe more than 15 minutes, okay? So if I wanted to get the equation of the voltage across the capacitance here, we're gonna go basically through the formula that we used before, V initial of 0 minus V capacitor of 0, V capacitor of infinity, e to the minus t over tau plus V capacitor of infinity. Okay. So basically at t, basically V0 is equal to 230. V infinity is what?
0.
0, right? And this is 0. So basically what you're going to end up with is an equation that says that the capacitor voltage would be 230 times e to the minus t over 1,000. You want to know when that will be equal to 60 volts. Okay, so basically what you're going to have to do is basically just compute the t here, because this is the only unknown from this equation. Okay. So basically, whenever you have a leakage resistance, you assume that you have a discharging circuit like this, and basically get the tau, the time constant, and basically get the equation for the discharging of the capacitor. And basically, if you want to get when the particular voltage will be reached, it's very easy for you to do that. And actually, there are some problems, other problems actually, when I tell you that at t equals to, for example, 1 hour. Compute V of VC. Okay. So basically, it's the opposite here. What you're going to have to do here is just get that 1 hour equal to 60 times 60 seconds, and basically just plug it in here, and basically get the value of VC of t at this particular time. You have any questions? Okay, let's go back. It's important also to have variable capacitors. Capacitors are usually used for such applications as, you know, the resonance circuits. Have you heard about resonance circuits?
Yes.
When you have capacitor and inductor, you have a particular resonance at omega is equal to 1 over LC, right? 1 over square root of LC, right? So basically, when you have, it's very important to have circuits like this for such applications as if you're sending something through the air. For example, if you have radio transmission, okay? How can you get a particular channel? Okay, you have all kinds of channels transmitted from basically the broadcasting antenna. You have all kinds of channels. Each channel has, or each radio station has a particular frequency. Okay, what you need to do is basically use a capacitor and an inductor and basically try to tweak them together so that you can actually match the resonance frequency of the station you want to hear and basically start listening. Okay, this was done before using a knob. basically you have something that looks like this. And basically, when you actually change a knob, you rotate a knob like this, you have here capacitor plates, and basically changing the position of this knob will change the area where the two plates are facing each other. Okay, so basically, if you look at this here, this is basically all the plates are actually in line with each other. So this is the maximum area. If I rotate it a little bit, you will have some of the plates actually not facing each other. Okay, so basically you'll have a different capacitance when you do that. This is a kind of mechanically variable capacitor. So basically, if you change the position of this knob here, you'll have a capacitance that changes with the angle of the knob. Okay, you have a certain range for the capacitance depending on how many plates that you're using. Basically, this is a multi-plate capacitor, and depending on the angle, you have a different area, and basically this will change the capacitance depending. How many of you are using a knob to change the channels on your car radio? Okay, how many of you are using something like this on your car radio right now? How many of you have something like this, like a knob like this on your phone? Usually mobile phones have a radio, right? Most mobile phones now have a radio, okay? So do you have something like this on your phone to enable you to change the channels? I don't think so, right?
No, doctor.
You do that digitally now, right?
Yes.
You just have a button and basically flip through the channels just by the press of a button, right?
Yes.
How can they do that? How can they have a variable capacitance basically that can change electronically? Actually, there is a very, very nice device called electronic variable capacitor, which is called sometimes it's called varactor or varicap. Varactor, variable capacitor, basically, or varicap, variable capacitor. Basically, they are both used in describing this kind of component. Basically, it's a very simple idea, but it's very effective. People found that if you have a regular diode, you have PN semiconductors, and basically, if you have a reversely biased diode, you're not going to have a current flowing, right? If I put, let me draw it for you. This is the kind of ideas actually that you have to think about because actually they are really nice ideas. If I have a diode that looks like this, and basically I put a positive voltage here, what's going to happen? Okay, what's going to happen?
Open circuit.
Do you expect a current to be flowing like this?
No.
No.
There is no current, right? Meaning that you will have positive charges here and negative charges here with a dielectric in the middle. The semiconductor actually in this case will act as a dielectric. And basically, depending on the voltage here, the voltage between these two terminals, you will have a different capacitance. People found that you can actually have different capacitance because actually you will have basically different reaction of the semiconductor to this particular voltage. So what people did was to use exactly this idea and basically have basically put they call like when you have a lower bias voltage, you have a smaller depletion zone, and basically means that you have a higher capacitance because you have a smaller separation, have a smaller X. Okay, and if you remember, the capacitance is equal to epsilon A over X. So here, when you have a smaller depletion zone, smaller dielectric, basically, you will have a higher capacitance. When you have a higher bias voltage, you have a higher depletion zone, meaning that you have a lower capacitance. So basically, depending on the voltage, you will have a different capacitance. And this is actually what is used in electronic tuners, on TVs, on radios, on mobiles, on everything. Okay? So basically, this is a very nice way of changing the capacitance without having to have a mechanical component involved. It's very difficult to imagine a mobile phone or now even TVs now are usually operated by a remote control now. You don't imagine to have something like this. You don't imagine even to have, some people can think about having a motor that is controlled by the remote control. Actually, you don't hear noise when you're changing the channels on TV. So basically, you don't have any mechanical variable capacitors any longer for these applications, at least. It's still used for some limited applications, but actually in the broadcasting and the tuning applications, most people now use the varactor or varicap. Please go ahead if you have a question.
So the capacitance in these types of capacitors are controlled by the voltage.
Yes. So basically what you do is electronically you change the voltage, and this is very easy actually. What you need to do is if you worked before with an Arduino or something like that, it's very simple in Arduino to generate a particular voltage. Okay, it's very easy to generate it using a software. So basically, you're going to generate a particular voltage using software in a microprocessor or a microcontroller, and basically feed that to this particular component, the varactor, and basically this will change the tuning of the tuning circuit that this varactor is used for. So it's very easy to do that with a software rather than having to have a mechanical knob moved or something like that. Okay. So this particular component actually is one of the questions. I believe this is one of the questions in the project. So basically, what you're going to be asked about is probably to find a real component, real varactor component. And it's very simple, actually. If you go to DigiKey and search for varactor or varicap, you're going to find quite a few. Okay, so here, as we saw before for variable resistors, we have also variable capacitors. And here we have variable capacitors as either mechanically variable or electronically variable. And basically, electronically variable capacitors are much more popular these days. Okay. The last application I'm going to talk about, last part of this lecture, is basically an application for the DC shock defibrillator that we talked about before. Basically, it's exactly the same idea that we talked about. What you're going to do here is you actually store a particular energy in the capacitor, and you discharge it as usually you use like 360 joules. 360 joules, by the way, is the standard of energy used by defibrillators. Basically, there are several types, but actually the maximum you can use is 360 joules. Okay, if you apply these across the chest of the patient, you can actually have enough energy so that you can actually reset the electrical activity in the heart. Sometimes, basically, it's like I saw some nice cartoon actually that probably I'm going to share it with you in the resources. Where actually they basically make an example, or basically give a model of this as if you have a classroom full of students and each one is talking to his friend or talking separately on his mobile phone. So basically you have noise. You're not going to have a common voice that you can hear. You cannot make sense of what people say in the classroom. Okay, so what you do in the defibrillation is just put enough energy to silence everybody, so that when they start again, they start in sync. It's very important for the heart. Is basically the synchronization of the different parts of the heart is basically the most important. Things happen in the heart with a particular sequence. You actually pump the blood from the atria, from الأذين لغاية البطين, okay, from the atria to ventricles at certain times. You cannot have both the atria and the ventricles pumping at the same time. If you do that, the heart will never work. Okay, so basically the sequence can be retrieved by actually passing this kind of energy through the patient. The only way to do that right now, the only technology that people use is simply have a device like this with a capacitor like this, basically, and this capacitor will be charged by a very simple charging circuit. Basically, this whole equipment, actually this piece of equipment, has basically two different functions, two basic functions. The first one is to charge this capacitor, And the second one is basically through these paddles. It's just to apply the charges or basically discharge the capacitor through the chest. Okay, so basically the whole system actually is based on a capacitor like this. In order for us to know exactly how the voltage rating of a capacitor like this should be like, we should remember that we have energy is equal to 1/2 CV squared. So if I have a capacitor that like this, this is actually one actual capacitor that is used in defibrillators. It has a capacitance here of 32 microfarads. Okay, so if I put this here and compute the V, you're going to find that the V should be about 4,743 volts. The rating of this capacitor, as you see here, is 6K volts. Okay, so this should be enough. Okay, so basically you charge this capacitor and discharge it through the patient in order for you to basically get this to work. So basically just it's a very clear application of capacitors in actual devices. Of course, as I told you before, there is a very clear application in each one of the tuning circuits that you use for your radio, for your TV, for whatever, okay? But actually, this particular application is very interesting because you're charging the capacitor to a very high level, to very high voltage, okay? One thing I needed to, or at least I have to emphasize here again, is that some people think that if you have a DC voltage, you're not in any risk of electrocution. Okay? يعني مش هتتكهرب لو لمست حاجة فيها DC voltage. Actually, this is wrong. Okay? If you have 6 kilovolts, if you have this kind of voltage, this high voltage, and if you basically touch this particular, if you somehow put your finger basically between these two, basically these two leads of the capacitor, basically your skin resistance is about 50 kilo ohms, about 30 kilo ohms. Okay, it's not much more than that, and actually it's much lower actually if you have a wet hand, if you're sweating or something like that. It's even much lower. Okay, so basically if you put your finger between these two, you're very likely to have your basically whatever part that you put in between these two leads, it's very likely to get burned because a very high current will be passing through this. Okay? If you touch it in a way where you have a hand here, one hand here, and another hand here, this current will flow through the heart. Okay? There is a big difference of putting these paddles across the chest and applying this energy basically to basically reset the electric activity in the heart, and basically putting your hand, basically if you touch one paddle with one hand and another with another, okay, with the other hand, the current that flows through you can kill you actually. It's very dangerous. So basically be sure that when you're working with a capacitor like this, when you're working with a device like this, before you actually open it and try to do anything with this capacitor, you try to discharge it first. Okay, make sure that it's discharged. Okay, otherwise you can be in danger. Okay, so basically this is one of the important things that I wanted to talk to you about. Electrical safety is not just for AC. Whenever you have a high enough voltage like this, you have to be really careful around it. Okay, is that clear? By the way, another thing about the defibrillators, if you saw some movies where people actually play with things like this, like comedians, where they actually just apply this and basically get a shock or something like that, it's like a fun thing to do or something like that. This is actually not fun. This is actually a life-threatening situation. It's not. It's meant for a situation like this, basically to correct situations like this, and actually it's not guaranteed actually to actually work each time. So basically you have this 360 and there is actually a protocol where you apply it once and basically wait for a long time and basically do CPR, like you have to do some heart resuscitation. You basically pump the heart manually for about a minute and then apply again and so on. If you have somebody with a normal rhythm and apply an electric shock like this, you can actually get to this particular part. You basically can get ventricular fibrillation. So basically, you can turn a normal rhythm into an abnormal rhythm with an electric shock that wasn't necessary. So basically, this device was not meant to be played with. They are really serious. They are actually life-threatening if they are not used the proper way. So basically, make sure that you don't really play with things like that. If you have a high voltage, you have to actually be really careful around it. Okay? Okay, so let's go back and look at the final problem. The final problem is the homework. Basically, this problem here we haven't talked about. Actually, this is a much simpler problem than the problem that we saw in this particular part. This is actually talking about the transients when you put a particular, when you charge a particular capacitance and then discharge it and so on and so forth. Here you have a 10 microfarad capacitor in series with a 10K resistor connected across a 500 volt DC supply. And then you charge it fully. You leave it like this until it's charged fully. Then you have 500 volts on this 10 microfarad capacitors. When you do that, you basically connected to a 1000 ohm resistance in order for you to discharge it. He's asking you first about the initial value of the charging current. Let me try to draw it for you. Basically, what you have here is that the charging circuit will be like this. Let me probably. Okay. You have the battery here, and you have a resistance, and you have the capacitance. Okay, this is 500 volts, and this is 10K. And this is the capacitance here is 10 microfarads. Okay, it's initially uncharged. Okay, so he's asking you first for the initial value of the charging current. If I have here a 0 voltage here, I have 500 here, then the current here, the initial current here would be what? The initial current would be what? I of 0 will be what? 500 minus 0 over 10K, right? This is the initial value of the charging current. The second question is asking about the initial value of the discharge current. The discharge current is a different circuit. Okay, and please, when you have a problem where you have charging circuit that is different from a discharging circuit, please draw the discharging circuit separately. So you have now this same capacitor with 500 volts connected across a resistance of 1000 ohms. Okay, and he wants to know exactly how much current, the initial current here will be what? What the initial current here is going to be like? In this
500 over 1000.
Yes, I discharge will be at 0, will be 500 over 1000 ohms. That's it. The last part is actually what we talked about earlier in the lecture. The amount of heat in joules dissipated in the 1000 ohm resistance. Basically, you're assuming that this will remain until this capacitor is totally discharged. So basically, you want to know, by the time this is completely discharged, you want to know exactly how much heat was generated in this particular resistance. How much would that be? How much heat would be generated from this particular situation?
V square over R?
No, actually 1/2 C V square. That's what we said at the beginning of the lecture, actually, because actually, if you want to do it this way, you have to compute the current or the voltage, basically, and basically integrate that with respect to time. You integrate, for example, V square over R with respect to time in order for you to get that. It's going to be a long problem, and you already know that the total energy will be exactly the same as the initial energy that you have. this electrical energy, the electrostatic energy that was stored in the capacitor, will be converted to basically heat energy in the resistance. So basically, it's going to be equal. Basically, this energy over the capacitor will be actually equal to exactly the heat energy generated from the resistance after fully discharging this particular capacitor. Okay?
Yes.
So please try to solve the homework, and please let me know if you have any questions, okay? One very important note I have about the last homework. So many people actually didn't look at the codes properly. If you have a six band code, let me clear all drawings and get that. We actually give this code for a reason, actually. You have to actually look at it very carefully. You have a case where you have 6 bands, you have each one of them is designated a particular value or a particular code. And basically for the 4 band, it's different, and the 5 band, it's different. Some people actually didn't know how to apply these for some reason, okay? So basically I gave them comments, please go ahead, please make sure to understand how to apply this. Okay, because if you don't understand it, then all the values that you're going to generate are going to be incorrect. Okay, so for example, for some reason, some people actually multiply here by a 10, by a different, basically like a 10 more than this. So basically, when you have black, they multiply by 10, and when you have brown, they multiply by 100. Okay, I don't know why. And actually, what we said also about the codes for the other values for the when we have these kind of resistance, when we have these kinds of, let me get to the example that I have. There was an example here. I don't see it. But anyway, basically when you have components like this, okay, what you need to do if you have like a 3-number code here, you need to apply the same exact code you applied for the 3-color resistance. Okay, so when you usually have here either three-number code or a 4-number code. Okay, whenever you have a 3-number code, if it doesn't have R, then you take the numbers like this, for example, this is 391, it's going to be 39 times 10 to the power 1. 10.3 is going to be 10 times 10 to the power 3, okay, and so on, okay? So basically you apply the corresponding code from here, the corresponding code from the 4-band or a 5-band or the 3-band, if you have a 3-band, okay? 3-band is basically the 4 without this tolerance part. The tolerance, if you don't have a 4th band here, the tolerance we said that's going to be 20%. And this is one of the comments that so many people actually didn't do. If you have a 3-band resistance, you can get the value like this, and you know that, and you have to mention that the tolerance is going to be plus minus to 20%. Okay? So please review this code again. If you have any problems understanding how to compute the resistors, please let me know. I put some feedback in the last homework, but actually, if you still need some help, please let me know. Okay?
Doctor.
Yes.
In the surface-mounted resistor, if it has 4 digits,
yes,
we still count it as like 3.
Basically computed for 4 digits. Basically, the surface-mounted, they do not have tolerance. They do not have digits for the tolerance. Okay, so basically assume that you have 4 digits like this. You have 3 numbers times 10 to the 4th. Okay. Because basically it's different. It's basically you don't have any way of basically having the tolerance there in the code.
And Doctor, the resistor down below, like the 5-band resistor.
Yes. Actually, there's a band here, but it's not very clear. Okay. You see it as nothing, right? Actually, there's a band here in the middle, okay? There's a fourth band here, but it's exactly the same color as the cielo, basically. So basically, it's not very clear. It might not be very clear on the screen. So you have the first 3 digits times 10. It's exactly like this, actually, but you don't have the one with the temperature coefficient. So basically, it's going to be 1, 2, 3, 4, 5. Okay. So you work with it as if it's like a 6-band code, but without the temperature coefficient code. Okay. So please review that and let me know if you have any questions. Inshallah, on Thursday, I'm gonna give you the exact what we're going to do exactly in the lab, and basically, hopefully, inshallah, we'll finish it by next week, inshallah. Okay.
Okay.
Any questions? Okay, so I'll see you inshallah next week. I'll see you inshallah on Thursday, inshallah, at 1.
Thank you, Doctor.
Shukran. Salam alaikum.